Hello guys, let's talk about freezing point depression. So the freezing point is the temperature at which the liquid and the solid phases are going to be at equilibrium. So their vapor pressures are going to equal to each other. In a solution, when we have non-volatile solutes, it's going to be harder for the liquid molecules to escape into the gas phase, so the vapor pressure of a solution is going to be lower than that of a pure solvent. And because the vapor pressure is lower than a solution, it is going to require actually a lower temperature to reach the vapor pressure of a solid, so the freezing point is going to be lower too. And substances like sodium chloride, magnesium chloride, potassium acetate, and others are used to prevent ice formation and to remove snow and ice from roadways in the winters. Now, this change in freezing point actually directly proportional to the concentration of the solute particles. It is very similar to the boiling point elevation. So when you have a pure substance and you add a non-volatile solute to it, your boiling point is going to get higher and your freezing point is going to get lower. Okay, I hope this makes sense. So the freezing point depression actually equals to the Van Hoff factor, which is going to be simply the number of particles a substance becomes when it dissolves, multiplied by K sub F, which is the freezing point depression constant, and the molality of the solute given right here. Okay, so let's take a look at some examples. Let's try to figure out which of the following zero point 0.1 mole aqueous solutions will have the lowest freezing point. So the biggest change in freezing point. Here we know that it depends on the molality, which is actually a constant right here. We have the freezing point depression constant, which is again a constant. So delta T sub F is only going to depend on I, on the Van Hoff factor. So how many particles we are going to have when we dissolve a substance. So if we start with potassium sulfate, if it dissolves in water, we are going to get 2 potassium ions plus a sulfate ion, right? So I in this case is going to equal to 3. What about KCl? So here we are going to get potassium ions and chloride ions, so I is going to equal to 2. Glucose is a molecular compound, so in this case, I is going to equal to 1 because it's not falling apart to any additional ions here. Iron 3 chloride, so we are going to get Fe3 plus 3 chloride ions, so I equals to 4. Aluminum sulfate, we are going to get 2 aluminum 3 plus ions plus 3 sulfate ions, so I equals to 5. And potassium chromate, we are going to get 2 potassium ions and 1 chromate ion, so overall I is going to equal to 3. So where will we get the lowest freezing point? Where the I is the largest, right? So right here. So the aluminum sulfate solution is going to give us the lowest freezing point in this case. Which solution will give us the highest freezing point? Glucose, right? So this doesn't mean that we are going to have a freezing point which is as high as the freezing point of water itself. It's still going to be lowered, but it's going to be higher compared to all the other solutions listed here. So this is going to give us the highest freezing point. Okay, let's take a look at another example. So here we actually need to figure out which one will have the highest freezing point, and we have the different molarities given, and we also need to figure out the Van Hoff factor. So K sub F is a constant, and we will need to multiply the molarities with the Van Hoff factor to figure out how big is the change in the freezing point? So in the first case, we are going to have a 0.10 mole of potassium sulfate solution. So we have I equals to 3, right? So this is going to be 0.30 mole. In the second case, we are going to have a 0.5 mole potassium chloride solution. So that's multiplied by 2. So that is 1.0 mole. Then we are going to have a glucose solution. So 0.25 mole multiplied by 1. So that's just 0.25 mole. Then we have a 0.15 mole iron 3 chloride solution. So that's multiplied by actually 4, right? So that is going to give us 0.06 mole. And then we have the 0.30 mole aluminum sulfate solution. We need to multiply that by 5. So we are going to get 1.5 mole. And here we are going to have a 0.20 mole potassium chromate solution. So we multiply that by 3. It's going to give us 0.60 mole. Okay, so let's analyze what we got. Where will we have the highest freezing point? Well, in case of glucose, right? Because that is where we got the smallest volume. So here we are going to have the highest freezing point. Okay, where will we get the second highest freezing point? In case of potassium sulfate, right? So this is the second highest freezing point. Why? Because when we multiply I with the molality, we are going to get the second lowest number. Okay, where would we get the lowest freezing point? In case of the aluminum sulfate solution, right? Because we have the highest number there. So this would give us the lowest freezing point. Okay, I hope this makes sense. Let's do one more example. Here, we have to figure out the freezing point of a 0.8 molar potassium sulfate aqueous solution when the mole freezing point depression constant of water is given to us. So we know K sub F, we know the molality, we can figure out I. So from here, we can calculate the freezing point depression, T sub F, which is going to equal I in this case equals to 3, right? Because we have two potassium ions and a sulfate ion. So 3 multiplied by our constant, 1.86 degrees Celsius divided by molality and multiplied by the molality, which is 0.80 mole. So if you do this calculation, you are going to get 4.46. What is the unit? Well, the modalities will cancel out, so you get degrees Celsius. All right. Now we need to figure out the freezing point of the solution, but we are missing the freezing point of the solvent. What is the solvent in this case? Water, right? What is the freezing point of water? 0 degrees Celsius, right? So T sub F of our pure solvent equals to 0.00 degrees Celsius. Now we can calculate the T sub F for the solution, which equals to 0.00 degrees Celsius minus 4.46 degrees C. So the overall freezing point of the solution is going to be minus 4.46 degrees Celsius. Okay, I hope this makes sense. See you in the next video.